everyone, my name is Ash, and in today's Roblox Studio tutorial, I'm going to be teaching you a new and improved method for saving player data. Now, I have made a previous version of this on my channel, but I wanted to make a new and improved version. Since then, Roblox has added some new data structures that I'm going to be using in this video, and the first thing I'm going to do is prove to you why these data structures that Roblox added recently are better than tables, and I'm going to show you how you can efficiently store data using these structures. I'm also going to show in this video how you can manage memory and check your memory usage for your Roblox Studio scripts. So if you're interested in that, keep watching the video. I know I've been gone for ages. 8 months is a long time. However, let's get started with this new and improved database system. So in the previous video that I made on Roblox Studio data saving, we used an object-orientated approach to save player data using a player class, and the player ID is the key to the database. Now in this video, I'm going to contradict myself and say it's not the best data saving system in the world, and I'm going to prove to you why that is now. Now, in between the 8 months where I let my channel die, the Roblox staff introduced a new type called the buffer type. Now, the buffer type in Roblox Studio is similar to a byte array in Java, if anyone's used Java. The buffer type allows you to get right down to the machine code in your programs and make changes to the individual bits in your program. Okay, so before we create our database system, we need to do a little bit of memory testing and memory management to see if there's anything we can do to reduce the size of our database structure. Now, initially, I want to show you how you can see your own memory for any variables that you create, and then I want to compare buffers and tables together to show you which one's more efficient, and then create our database structure from that. So initially, I'm just going to create a number variable here, and I'm going to call it mynum, and I'm going to give it the type number, and I'm going to set it to 100. Now, this number would be stored in binary digits in the program's memory. And I guess a brief introduction onto binary digits, instead of the base 10 usual decimal numbers that you get, so you'd have the ones column, the tens column, the hundreds column, and the thousands column, and that creates the numbers that you see on the screen. Rather than saving it like that, computers will break it down into machine code, and this machine code is in base 2, so it would go from 1, 2, 4, 8, 16, 32, etc. And they're stored either as ones or zeros, so either they are included or not. So this is the binary representation of the number 100. So each 1 and 0 that you see on the screen is called a bit, and 8 of these are 1 byte. So as you can see, you can store the number 100 in a certain amount of bits. Now, to convert this number into the 100 you see here, you would start from the right-hand side of the byte, and you would check each column for a 1, and if each column had a 1 in it, you would add that to the total. In the 4s column, there's a 1, so you'd add 4. In the 32s column, there's a 1, so you'd add 32, and same with the 64s column. So that would add up to be a total of 100. So this is how our number here is stored, and you can actually try and view this in memory, even though you won't see much. So in Roblox Studio, how you can manage and see this in your memory, you would play the game, and you would enter the developer tools up here, and you go to the memory tab. Now, as we stored it in the server, you check the server, and obviously it looks absolutely horrible, but it should be underneath place script memory. And as you can see here, the mem script uses nothing, and this is because we're only storing 1 byte of memory. If I was to store a lot of numbers or a very large string, then you might actually see a difference there. So let's try and get that number to change. Let's change it to a string instead of a number. Let's change the string to be something huge. If someone could calculate what that binary number is, I'll pin your comment, but you're going to be there for a long time. Another thing that Roblox added recently is a debug method called the set memory category, and what this does is it allows you to categorize your memory in the memory tabs. I like this little indicator at the start so I can filter out the label. You can name this whatever you want, but I like to filter it out in the memory tab. So every frame, it's just going to add on more of the string. Okay, so now you can see the memory is actually fluctuating around a bit. It's going to keep increasing while we add more to the variable. Now, Roblox Studio does offer another tool in the F9 developer thing called the Lua Heap. This basically is a subset of memory, and you can only see certain things from inside the heap. If you go and click on the server, because we created a server script, we use the memory category here because we created a memory category and create a snapshot. You can actually see our string here has a size of 11,990 bytes. If I create another snapshot here, this should increase. There we go. So it's now 18,000. If you do more intensive work like storing a large volume of data, these strings can become very, very, very large very quickly. Okay, so the next thing I want to do is introduce the buffer type in Roblox Studio. So they have documentation on the buffer type. It allows you to store streams of bits and allows you to control the memory. So beforehand, the alternative to doing this was with tables. The buffer type has a lot of functions here, and the ones we're mainly going to be focusing on is the reading of the 8-bit number, which is read U8, write U8, which is writing an 8-bit number, and obviously you can do 16-bit numbers, 32-bit numbers. You can do floating point values as well. That's useful for storing vector 3s, UDIMs, anything with a decimal point. You can also write strings. This again will probably convert it down to the ASCII value inside of the buffer. But I'm going to show you some of these now, and we're going to try and compare them to tables. I'm going to remove this myString stuff and keep the while true do loop because we want to keep the variables that we create in the scope. If we just let the script end, then it won't be visible in the Luau Heap tool in the F9 developer tools. Instead of calling it var tag, we're going to call it the category buffer now, so we can see the difference. And in this, we're going to create a buffer. So to define a buffer, I'm going to call it buf, and I'm going to give it the type of buffer, and I'm going to do buffer.create. So when you create a new buffer, you need to give it a size, and the size, you cannot change the size of a buffer during runtime, so it needs to be defined up here. The size variable needs to be in bytes. So if you remember at the start, we said that one character contains 1 byte. So if we wanted to store 1 character, we'd put a size of 1. If we wanted to store the string hello, we'd use 5. For the moment, I'm going to use the size of 0. So we've created our buffer type with a size 0, which means we can't actually store anything in it, but I just want to show you what this creates in the memory tab. So if I go into the heap tab, I create a new snapshot in the server, we can go into the memory categories and you can see our buffer here. So we've got our buffer tag here, and you might be a little bit confused as to why there's 16 bytes here. There seems to be 8 bytes of overhead on the buffer, and when I set it to any size, automatically creates 8 bytes as well. So those 8 bytes plus 8 bytes equals the 16 bytes here. I will show you why. I've set the buffer size to a size of 9, so now there's 9 bytes being stored in the buffer. But as you can see, the size has only gone up by 1. So this table here on the screen will show you how much memory each buffer takes and its size. As you can see, if you only have between sizes 1 to 8, it's always going to be the same size anyway. Now this proves that there's 8 bytes of overhead and there's also 8 bytes of memory allocated to a buffer. However, let's compare that to a table now and see how much overhead a table has. So we're going to replace our tag here with the table tag now, and instead of a buffer, we're going to create a table type, and we're going to rename it to table, and the buffer here we're going to change to be an empty table. You can see that an empty table tag here gives us 48 bytes of memory. So without anything in it, there's already 48 bytes used up. Now this is almost 3 times as inefficient as the buffer's data type. In other words, it's not looking so good for the table right now. So let's try and add some data to this table then and see if we can increase the amount of memory usage. So I'm inserting now 3 numbers into the table. So as you can see, the memory has gone up to 112 bytes. And this is why the previous data store I made will have such an issue in the long run. If your Roblox Studio game has a lot of data to be stored, it's not looking good for you. Now just to make things worse for the table, I created 2 scripts earlier on, so they both store the numbers 1 to 255. You can see the buffer memory right at the bottom with 263 with that 8 byte overhead. However, the table memory tag is all the way up in the 4000 bytes, almost 4 kilobytes of memory. So this really kind of proves the point that buffers are more memory efficient than tables. And on the back of that, we're going to make our new data store system for your Roblox Studio games using these buffers now. Okay, so we're going to start building our new database system now, and I want to start off with the structure and how the system is going to work. Now, initially in our database system, we're going to start off with the server script, and that's going to listen for when a client joins the game. Now, when the player joins the game, a function inside the server script will fire, which notifies the database manager that it needs to be updating the data and restoring data from the database. Now, the data that we're going to be saving and loading from the data stores is actually a buffer type, so we're going to be sending buffers to and from our database system, depending on when the player leaves and joins the game. Now, where this becomes a little bit more advanced, buffers are actually immutable, which basically means that you cannot edit the size of a buffer once it's created. So when we retrieve this buffer from the database, we need to check if we need to add stuff to this buffer or remove stuff from the buffer, and this can happen due to a few scenarios. So for example, say I add a level attribute into the database and we want to save that in our next update. Once we roll out this update, there are going to be hundreds of players that join your game that do not have a buffer that can hold this level attribute. And if it does try and hold this level attribute, it would result in something that we call a buffer overflow, as there's too many bits trying to be stored in the certain buffer type. So to get around this, we're going to check first if we need to add more bits on or remove any bits that we've used before, and I'm going to show you how to set that up and how to use it. And once we've done that, we can write the read-write functions that write data into the buffers and read data from the buffers, and we're going to do that based on an ID system. So you'll give an attribute an ID and a size, and the size that you link the ID to will be a size in bytes, and this is the allocated memory you give it in the buffer. We're going to start making our structure in our new project in Roblox Studio. And the idea is once you've made it once, you can just copy and paste it into all your games and you'll be able to set up the new Datastore system using this. And I'll show you some use case examples at the end of the video to show you how to use the new systems in your Roblox Studio games. So to begin with, we're going to create a new folder in server script service because that's where our scripts are going to run at the start of the server. We're going to create a new folder. We're going to call it whatever you want. I'm going to call it Datastore. This Datastore folder will hold all of our scripts. And the reason we're doing it on the server, if you don't know already, is if you save data on the client will be able to change that data using script injections. Therefore, we want to save all of our data through the server. So the first thing we're going to need is a server script, and I'm just going to call it server. This is the script that will listen to client connections. Now, as a child of the server, we also need some module scripts. This is going to allow us to edit data in other scripts. This is why they need to be module scripts. So I'm going to call this one the data manager, and this is going to be where all the read-write functions happen, the updating of the buffers happen. The core of the database system is going to be inside this data manager module script. Now, what you can do is duplicate this module script and rename it to server store. Now, server store is just going to be a global table that you can access from anywhere. The table will store all of the player buffers, so you can access anyone's player buffer based on their ID. If any of you watched the previous video on data saving and data stores, we used the player classes table, and this is going to act the same way. Now, finally, for our structure, we're going to need a read-write functions module script that allow us to access some read-write functions. So I'm just going to call this RW functions. It's not the best name to call it, but it's going to be where we store all our read-write functions. So let's set these up now. Now, we're going to start off in the server script here, and the first thing we need to set up is our services. Okay, so in our server function, we're going to need two services, and that is the player service and the data store service. The player service is going to be used to detect a connection from a client, and the data store service is going to be used for handling data queries. And one thing I will mention is that you should go into the home section and go to your game settings, and in security, you want to enable API services access. It will allow us to access game services such as Datastore, so that has to be on for this to work. So make sure that's enabled in your projects. The next thing we're going to work on is the modules. Now, in this one, we want to reference both modules that we created, the server store module and the data manager module. So this is how we are going to reference the data manager and the player data store. So the player data is a table of buffers, and that will be where all the data is stored. And the data manager is where all of our functions that will process data will be stored as well. Now, we're going to do another section for constants, and our constant here is going to be our database. We're going to have this set to a type of data store. Now, this is basically instantiating our database here, and we've called it database, and it's a data store type, and we will request a new data store called player data, and this is where all our player data is going to get stored. Now, the next section of the server script is going to be the events, and in the events, we want to detect if a player joins or if a player leaves. So we can use the player service here to do that. We can use the player added event, and we can also use the player removing event. And we're going to connect them to two functions that we're going to create above that. So in our function section, then we're going to create two functions, and one of them is going to be the player joins function, and the other is going to be the player leaves function. Now, the player joins function is going to take in a player with a type of player. I'm not going to bother with the function types for these functions. I just don't think they're really necessary for this example. I'm going to try and keep this as simple as possible. We're going to add them to the connect events here. So we're going to have this one as the player joins. This one will be player leaves. Okay, so the next thing I'm going to do is indicate to the user in the output logs that the player has joined. So I'm just going to add a print here. I'm going to use a format string, and I'm going to say that the player.name joined the game. So what do we actually want to do in the player joins function? Well, when the player joins the game, we want to retrieve the data from the database. So how do we get data from a data store? Well, we have to use the database. So we're going to reference the database, and we're going to use the getAsync function to request something from the database. Now, we're going to use the player's ID again, but we're actually going to add something else onto this because we need to save 2 bits of data. So when it comes to requesting the data, I'm going to use the key of the ID and _D, which stands for underscore data. So this is going to return us a buffer. So another thing we need to save and retrieve in the player joins function is a data map. I'm going to show you here an example of why we need the player map. We're going to go back to our example of when we updated our game with a new attribute. Now, what if this new update included us removing an attribute? Now, if we remove an attribute in this new update, all of the buffers inside the data store at the moment are going to have different lengths and sizes to the new data buffer that has an item deleted inside of it. Now, we have to find a way of checking whether or not we should keep the old data and put it into a new buffer so that we limit the size of the buffer every single time the player logs on. If we we remove an attribute, then the default size should then be the size of the new buffer in the new update, not the size of the old one. So all of the buffers in this data store need to be converted to this new buffer. And the only way we're going to be able to do this is if we map the data from the old buffer into the new one, but also skip over the data that has been removed or added on. And the only way to do that is with a player map. And we have to save this old player map so that we can compare it to the new one in the new update. And that's how the update function will work in the future when we create it in the database manager. We're going to be retrieving our player map here, and it will be of type buffer. And we're going to want to retrieve something from the database again. Now, as an extension in this function, you could make this be two different databases and use the player ID as the primary key of each database. And by primary key, I mean the unique identifier. But for simplicity's sake, I'm just going to have it in the same database for now, which means that we're going to have to store it using the player ID with an extra little bit on top of that as well. So again, we're going to use the user ID. I'm going to do _m for map. Now, what if these don't exist? Well, we should add a little clause here that does something if these return nil. So we're either going to be saving this or we're going to be saving a new function. And inside the database manager, we're going to have a function called configure data buffer. So this or function here is going to run if a player is joining for the first time. And same for this bottom one. We're going to have another function in the data manager. Now, for the player map, we're going to have a default player map in the data manager called data size map. And this is going to be set up inside the database manager shortly. Now, the last thing we have to do here is save the player data into the player data table inside the module script. So we're referencing our player data module script, which we defined at the top, and we're using the player.userid as the reference, and we're going to set that to data. This is our data buffer here, which contains all of our personal data. Now, this then securely stores it into the module script, which is called server store. So that is all for the player joins function. For the player leaves function, we are going to do another print statement for debugging purposes. Okay, so once the player has left the game, we're going to try and save the data now. We're going to reference the database and we're going to set async, and we're going to use the same names that we used up here. For the data, we use player.userid_d as our primary key. We're going to save player data and then reference our player.userid. That's how we saved it in the player joins function. Now, for saving the map, obviously we've got to save the map as well. So I'm going to copy and paste this line. And if you remember, our primary key for the map was _m rather than _d. Now, we didn't actually save the mapping into the player data table. All we need to do here is reference the database manager, so the data manager dot data size map. But that's it for the events. Okay, so in the database manager, we're going to set up some modules. We're going to reference one module, and the module we're going to reference is the read write functions. The read write functions module is going to store functions that will write and read data to the buffers. We're going to reference our read write functions with a require, and it's just called script, and we're going to have to use quotes here because we gave it a weird name. But that is our script, which is inside of Datastore server and data manager. It's this script referenced here. Now, we will have a few constants in this module script. We're going to have something called the size length, which is a number, and that is equal to 1 at the moment. And we're also going to have an ID length, which is also a number, and that is equal to 2. You're probably wondering what these are. We need these to define how long our sizes are going to be. So I've given it 1 byte because we're not going to have a size of 255 bytes. I just don't believe we will. But this can be changed, and we also have an ID length here of 2 bytes. Now, the ID length of 2 bytes is going to be how many IDs are going to be stored in our sizes table. So I've given it 2 bytes, so you can have 65,000 attributes approximately saved into your database. You can increase this length based on how many you need. The next thing here I'm going to define is just the data manager table for the module script, and I'm just going to call it DM, and I'm going to return DM at the end as well. This is just for the module script. So before we write any of the read write functions, anything like that, we're going to create a few helper functions inside of DM. So the first function we're going to write is the sum of array function, which is going to take in a table. I'm going to call it table, and it's going to return a number. Now, I've increased the size of the text, so hopefully you can see that a little bit better as well. Another one we're going to create is the count helper function. And this function will also take in a table and return a number. The sum array function is going to get the sum of the attributes in the table, whereas the count function is going to get how many there are. Now, some of you that know a bit more about tables in Roblox Studio and Lua know that you could just do the hashtag table to get the length of the table instead of adding a new count function. There is a reason why I'm not using the hashtag. It's because if I give you two examples here, one of them is an array here, and one of them is not an array because it doesn't have an ordered index. So I've taken out numbers 2 and 4 here. You can imagine that this is what it would be like if you were removing old attributes, and the ID would be the index and the size would be the value. Now, as you can see, if I do hashtag table on both of these, this is the output that they produce. Now, for the first one, you can get the length of the array, but the second one doesn't actually work on non-orderable indexed arrays, which means to count the number in here, we'd have to make our own count function, which is what our helper function will do. Another thing we're also going to need is 2 variables. One of the variables is going to be the total data size. So this is going to be where the array sum comes in, and this is going to be the size in bytes of our current buffer. And this is going to be a server-wide thing because everyone needs to have the same sized buffer. Another thing we're going to need is the data size map, and this is something we defined earlier. So to recall, the data size map is going to be the server-wide data map. So the map is going to map IDs to sizes. So as we saw at the start of the video, we don't want to be using tables where we can help it. We're going to start off really simple, write the sum array function, and this is going to be our helper function to get the total of the table that we've passed in. So first of all, we need to set the totals to 0, and we're going to loop through each value in the table, and for each value we're just going to add v. Like such, we're just going to add v there, and then we're going to return total. Now be cautious when using this function, we haven't defined the types for table, and if we pass in a table that has string values, this will break, so just bear that in mind. It's very similar for the count. We're going to have a total there as well. We can actually copy and paste all of this here, but instead of adding v, we can just add 1 because we're just counting the number of elements inside of this table. So those 2 helper functions are complete. We can move on to the other functions now. So the next thing we need in our database is a function that will return a table with the sizes and the IDs of our data. Now I know I've been advocating on not using tables, but I think this is a valid point to make. Tables are better for readability, and in this case I think tables will be useful here because they're going to be in a local scope, so they're not going to be taking up loads of heap memory all the time, and we're not saving it to the database. The whole point of having an efficient database is there's not a lot of memory usage inside of that database, and our buffers will allow us to do that. So we're going to have a function here called getDataSizes, and the function here is going to return a table. So the type is going to be a table where the key is a number and the value is also a number. So this is our table type. This is what's going to be returned out of our table. So we're going to define our data sizes table here, and I'm going to show you what you can put into this to make our database work. And obviously what we're doing here is just returning it. So we're going to return data sizes. However, what does this data table actually get used for? Well, let's say we want to store a position of something here. In this system, what you're going to have to do is you're going to have to write in a new value. So let's give this an ID of 1. This is the ID column. So it's done based on ID and size. Let's say we wanted to store the player level here. So this is going to be the player level, and it's going to be set to the ID of 1. Now we're going to set our player level to have a size of 1 byte. So this is 1 byte of memory allocated to the ID of 1. So we can do that for the ID of 2 now, and let's say we want to store the string hello. That's going to be 5 bytes of memory allocated to the string hello. So the table here is basically for readability, so we can put in our own data IDs and put in how much size they're going to take in our buffer. By the end of this, you'll be able to take this out and kind of comment this out if you didn't want the ID of 1 to be saved. Same thing with this. But for now, I'm just going to keep it with these 2 here and the ID of 1 and 2. And another thing you'll be able to do as well is do ID of 12 here instead of having to put 2, 3, 4, 5, 6, 7. You'll be able to do something like this as well, which is quite useful. It means that you don't have to change the IDs of everything if you want to remove it. So for this example, I'm just going to leave it like this for now. We're going to try and store the level of the player and hello. So the first step is when the player first joins the game. This section is going to be making the functions that configure the data sizes map and the data buffer for players that just join the game. We're going to call this function the configure data size map. And this is going to be a function that returns a buffer and a number. So it's going to return 2 things. The number is going to be the sum of the size, so the total sizes that we defined up here, and the buffer is going to be the data size buffer that we can store up here as well. The other function we're going to configure is we're going to configure the default data buffer as well. This will be useful because it allows us to update the old buffers that are stored. It's just going to return a buffer. Okay, so the configure data buffer one is really easy. All we need to do is return a new buffer. But we did actually specify this earlier, and we use buffer.create to create a new buffer. And obviously, as I said, you have to give a buffer a size, and that is going to be our total data size. We use the total data size up here, and we're going to use it in here to create our data buffer. This is where all our player data is going to get stored. Configuring the data size map is a little bit more complicated. First thing we need is the data sizes from the data size table. So all we need to do is get data sizes because we've already defined that method above. So this is going to return our table of data sizes, which is a type of this. So we can actually move the type down here. Another thing we need to define is the new buffer. buffer. So we're going to call it a size map buffer. And this is going to be a new buffer. And again, we need to do buffer.create here. And now we have to figure out what the size of the buffer is going to be. Now, to figure out the size of the buffer, we need to figure out what this is actually storing. So for every data point in the data sizes map, we want to store an ID, we want to store the size. Now, thankfully, we already created two constants up here called size length and ID length. These relate to these sizes and IDs here. So all we need to do in this creation is we need to count how many data points we have and then multiply that by the size and ID length added together, because each attribute will take up the amount of bytes these are combined. So in this create, then we need to call our count function, which we define up here. So we need to do dm.count. And what table are we counting? We're counting the data sizes table because we want to know how many data sizes we have. And then we're multiplying that by the ID length, and we're adding on the size length. So this is the total size of our buffer, which will map sizes and IDs together. Now, the next thing we have to do is actually fill in the data, because at the moment we've created a buffer with that size. However, all the values inside of that buffer will equal 0. We need to fill in our buffer with all of this information. So we're basically mapping this into this buffer. So to do that, we need to define a new local variable called offset, and that will equal 0. Now, the offset variable is going to track where we are inside of the buffer and will allow us to change bytes at that offset. The next thing we need to do is loop over this data sizes table. So we're going to use another for loop, and we're going to start from 1 because tables index at 1. And we're going to use a function called table.maxn, and table.maxn will loop through this whole table and say, for example, we had 20 here, then it will go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it will loop through each one and see if there is a value stored in that ID. The table is going to be our data sizes table. So the first thing we need to check if it's equal to nil. So as I said, if we had a data type that's got ID of 20, IDs number 4, 5, 6, and so on are going to be nil. So we need to make sure that that's not the case. But if it is, we can just continue on and ignore it. If the value at the index in data size is equal to nil, then we can continue and end the process. Okay, so the next thing we need to do is we know there's a value, so we need to store our ID and size into our map. So how we're going to do that is we're going to reference our read-write functions now. And obviously these aren't going to be defined yet, but they will be defined shortly. And inside of the read-write functions, we're going to create a function called writeID. And this function is going to take in the size map buffer, and it's also going to take the offset variable and the index, which is the ID. So the I is the ID, the offset is where we are in the buffer, and the size map buffer is the buffer itself. The next thing we want to do is change offset, and we're going to add the length of the ID, so ID length, to the offset. And what this will do is it will move us from where we're storing the ID to then where we're storing the size of the data. And then we can do the same thing again where we copy and paste this, and instead of write ID, we're going to have another function called write size. And instead of offsetting by the length, we want to offset now by the size length, because they are different things. These could be different values, so we can't just offset by the same amount each time. And also in here, we're not storing the ID anymore. We are storing the value, which is the size. So we need to do data sizes I, which is the value that we're going to be storing. And once that for loop's end, we can just return size map buffer, and we can also return the sum of data sizes. So this will be the total size of the new data buffer, because obviously if we have the total size of this data sizes, we know that we're going to be using 6 bytes of data to store all of our attributes. And so if we just do dm.sumArray and we sum our data sizes table, then we should get back the correct value for the size of the data buffer. So that is it for configuring the data sizes map and the buffer. We are going to come back to the data manager, but we're going to define those functions in the read-write function module script now. Okay, so we've got a new empty module script, and that's our read-write functions, and we're going to call this RW functions just so it relates to the name of the module script itself. Okay, so in this section, we're going to define what our write and read ID and size functions are going to be. So we're going to need 2 variables stored here, which will be stored as functions. We're going to need a read ID and a write ID. Now, these are going to be our buffer functions that write to the database based on our sizes. Now, in the document that I wrote up in the description, I will put the corresponding functions for the sizes. If you change the size of these 2 variables in the data manager, these functions will also have to change. So at the moment, the ID length is 2. So we're storing 2 bytes for the ID length. So to write the ID length, we're going to have to use read u16, because we're storing a 16-bit unsigned integer. Same thing goes for the read. So obviously for the write ID, we're going to use the write U16, and for the read, we're going to use the read U16. So we're going to be writing an unsigned 16-bit integer and reading an unsigned 16-bit integer. Same thing goes with size. So if I copy and paste these two, we're going to have the size one as well. So for the size, in our data manager, our size is at length 1 rather than 2. So instead of using 16, we're going to be using an 8-bit unsigned integer. So that just needs to be 8 bits there. Now we actually do have another function here that we're going to define now that we'll use later. And we're going to call it getRead function. And this is going to take in a size and return any. So this is going to be used when we read data. And to read data, we're going to need to know what function to use to read from the buffer. The size variable here is going to determine what function to use and what attributes and arguments are going to be needed for those functions. We're going to start off with another locally scoped table, and this is only going to be used in this function, nowhere else. So it's not going to take up a lot of heap memory at all. It's going to be garbage collected. This read functions table here is going to store 4 functions, and that'll be these functions here: buffer.readU8, read. So all the different read functions we can use, I think, are going to be applicable for this database system. For an extension, you could actually change this function and add extra ones, so you could read negative numbers, or if you wanted an unsigned 32-bit integer instead of a floating point one, you could change this as well. So as an extension, I do challenge you to do that. And the reason I've given this an any type to return is because we're actually going to return a function, and we're going to define this function as the size function. And this size function is going to be an if statement, and we're going to just double check first if we can actually find a function using read function size, because obviously if you pass in a size here that's not in this table, there won't be anything. And if that is the case, then we're actually going to define a new function to return here. The function is going to take 3 parameters. B is going to be for the buffer, O is going to be for the offset, C is going to be for the count, and all that's going to do is return read functions of size BO, so the buffer and the offset. So what this function here actually does, when you call this function, it actually returns the read function and actually calls that function using the 2 parameters here. And the reason why we have to do this is because we also want to be able to save strings, because a lot of people use strings and save strings in their databases. So obviously if the size is like 20, it's pretty obvious that you're going to be storing a string or something along that line. So if the size is not in the database, so if we are not storing an 8-byte number, then we want to be storing a string, and that's where this count comes in. So after this function here, we're going to use an else, and we're going to create another function. It's going to be very similar to this. So you can just copy and paste the function here, but instead of returning the read functions, we're going to be returning buffer.readString function. And this takes in 3 parameters. As you can see here, it takes in a count as well. So we're going to pass in C to that one as well. So the first function here actually doesn't use the count, but that's now defined as our size function. And then we can return that function just like so. And when we go to call this size function, we will just need to pass in our B, O, or C, and that will allow us to read our data based on the buffer, the offset, and the count. Okay, so that's all for the read-write functions. You can actually close this down now. We won't need to do anything else in the read-write function. We're going to be working back in the data manager now, and we're going to start on more data functions. Now, in order for us to read and write data, we're going to need a way to get the memory address and location of the data, or where we need to store the data. So we're going to create another function called getMemoryAddress. Now, this memory address function is going to return 2 any types, and it's going to pass in a couple of types here. First of all, it's going to pass in a buffer called map. Now, this is going to be the current map based on what map was chosen when the user joined the game. It'll be our user's map, and the ID to find is going to be the ID that we're trying to find. Say we're trying to find our hello string here in our database. We know that we're trying to find ID of 2. So we do need to define a few locally scoped variables. So we need to define an address, and that'll initially be 0. We need the offset again because we're looping through the map buffer. I'm also going to create a local variable called map size, and this is going to just be the size length plus the ID length. I said earlier, this is the size, the total size used in the map buffer for one attribute. Each of these are going to use 1 map size length in bytes. So now we need to loop through the map buffer until we find the ID that we're looking for. And the best way to do that is with a while loop, and we're going to check whether offset is less than the size of the buffer. And to check the size of the buffer, we can do buffer.length map. This loop is going to run until offset is larger than the length of the map. And if it's larger than the length of the map, then we know that we haven't found the ID that we were looking for. And if we can't find the ID that we were looking for, we're just going to return 2 nil values. Now, to get the ID, we need to read from the buffer map. So at offset 0, we're always going to start off with an ID, because obviously when we configure our data size map, we save the ID first. We save it at address 0 or offset 0. So the way we're going to do that is we're going to get the ID by doing our read-write functions, which we wrote a minute ago, and we're going to read the ID. We're going to pass in our map and the offset that we're at currently, which is our offset variable. So this is going to read, based on the size of the variable up here, it's going to read our ID of the first element. We also need to read the size. We need to change our offset so that we move along in our buffer. Now, our offset is going to be equal to the ID length. So we're going to add on the ID length to the offset. Now, to get the count variable, or how large it is, we can do read-write functions.read size of the map and offset. And again, these functions we just defined in read-write functions. They are only buffer functions. Now that we've read the ID and the size, we can now check if the ID that we've read is equal to our ID to find, which we defined in the arguments. And if it is, then we want to return the address that we're currently at and the count variable. The next thing then we want to do is add on to the address, because we've now moved inside of our buffer. So we're going to increase the address by the count number, which is our sizes number. We're also going to change our offset here to add on the sizes length. Obviously, we did this with the ID length up here. We also need to add on our size length to get to the next ID in the buffer. Now, this is all we need to write actually for our function, for our get memory address function. This will return the address and the size of the ID from our map. So now we can move on to actually reading and writing data from our data buffer. So I'm going to create a new function called write data. We're going to do the write one first. Now it's going to take in quite a few things here. So we're going to first take in a buffer, which we're going to be writing to. We're going to be taking in the ID, which is a number, and the ID will correspond to the ID that we want to write to in here. So if we want to write a string, then we would use the ID of 2. Say we wanted to write something other than hello, we can use the ID to reference this part of our buffer. Now the write data is also going to take a function, and this function is going to be our buffer function. So are we going to be writing a 32-bit number, a 64-bit number, an 8-bit number, anything like that? This function is going to be passed in. You can mitigate using this function parameter by doing something similar to this. So that, I guess, is another extension for this system. And the final thing we need to take in is the actual data that we want to write itself. So this can either be a number or a string based on our setup. So the data type for this is going to be number bar string, and the bar here kind of acts as a OR. So the write data one is quite simple actually. So to write data into our Roblox Studio buffers, we would first need to get the memory address that we defined. So we need to get the address and the count, which would be our size, and we need to reference our get memory address function that will take in our data size map, which is the map that we're using, and an ID, which is the ID that we passed in. This is going to get the address of the offset of the data that we need to write to. So the last thing we need to do here is just add it to our buffer, and the way we're going to do that is by calling the function f, which we passed in to the parameters. That is going to obviously have 3 parameters. That is going to be our buffer that we're writing to, the address that we're storing it at, and the data that we're storing. And that will store our data, whether it's a string or a number, into our data buffer. Now, for the read one is a little bit more complicated. So we're going to read data, and it's going to be a new function, and it's going to take in a buffer. So we're going to call it B again, and the ID that we want to read. So say we wanted to read our hello string here, we would have to reference the ID of 2 from our data buffer. And this is going to return an any type. Now we're going to do the exact same thing again. We're going to get the memory location of our ID from the data map. Once we have this address, we can then go to that address in our data buffer. We can read the data at that address based on the size variable that we've passed in here. So if address, because we want to make sure that address is a thing and not nil, we want to return, and we want to do another read-write function. And this time, this is why we created getRead function. We're going to take in our count as the size. This is how many bytes we want to read. So if you recall, this function actually returns a function. So we're going to call that function, and we're going to pass in our buffer, which is B. We're going to pass in our address, which was our O, our offset, and our C is our count. We can end that there. We can return false if the data was unable to be read. You could throw an error here if you wanted to. It's completely up to you in this case scenario. So these two functions here are going to read and write data to our data buffer. Now the final function we have to write is the function that deals with stuff like changing the data in here after an update. So I mentioned earlier that you could have something like this where you've defined 20 different IDs, but you want to remove this one here. We need a function that will deal with stuff like this and removing it from the old buffer and making sure the new buffer has the right amount of bytes and we don't lose any important data. So how are we going to deal with something like this? Well, we're going to create a new function, and it'll be our last function called update data. And this function is basically going to scan all of the data here in data sizes, and it's going to compare it to the old data that has been stored in the database before. So we need a reference to the old database. So the old data is going to be of type buffer. So this is going to be our old player data that the player loads in. And we also need a reference to our old mapping, to our old player map. And we're going to just call it old mapping. It's going to be another buffer as well. These are both of the buffers that we will get from the player joining event in the server script. Now, in this function, we're actually going to configure our data buffer now. So what we're going to do is we're going to create something called new data. And this variable here is going to be our new data buffer. So as I mentioned earlier, we also need a reference to our data sizes table. What I'm going to do is this time, I'm going to just put it into the for loop. So we're going to loop through each ID, and we're going to use this table.maxNumber function again. And we're going to get the data sizes. We're going to loop through every value in the data sizes table, including the ones that are nil. And we're going to do some comparisons on the memory addresses. So the memory address function here is really important. So we're first going to get the memory address of the old data. So we're going to do, and the old count. And that's going to equal dm.getMemoryAddresses. And we're going to get the memory address of the old mapping and ID itself. So what this here is going to do is it's going to get us the old address and the old count, whereas this new address and the new count is going to get the memory address, but instead of the memory address in the old mapping, we're going to use the new mapping. We are going to reference the data size map that is inside of DM. Now, we're going to check a few conditions here, and this is quite basic. And if you wanted to add on to this to make it a little bit more advanced, you could. This is where you would do it. We're basically going to check if the address of the ID doesn't exist in the new data set, then it means it was removed, and we can just skip over and ignore that value and not add it to the new data buffer. So if new address is basically nothing, then we would continue and skip over this ID. We would not store the ID if the new address doesn't exist. Now, we're going to do the same thing with the old address as well, because if the ID is not in the old address, it means that in the new update, the item has been added to the sizes table. And that means there shouldn't be a value in there anyway for that, and that gets ignored and set to 0. And the final thing we need to check for is if the count has changed to the size of the ID. And this will only happen if I save the data with this data sizes table and I change this to be a 6. It would change the count size because I've changed the size that this ID will take in the buffer. Now, if we do this, we want to also continue. So if they are different from each other, then we're going to continue. You can definitely make this a little bit more optimized for an extra challenge. If all three of these cases don't check out, then we know that we can copy over the old data into the new data and use the new size as the size of the buffer. So to do that, the buffers actually provide a really useful tool called buffer.copy. It allows you to copy over from a source to a target based on an offset. So the target in this case will be our new data, because we want to copy over the bytes from the old data into the new one. The address that we're going to be targeting is the offset. This is going to be the offset or the new address of the data with that particular ID. Now, the source is going to be from the old data buffer, and the offset is going to be the old address. So the old address of that data in the old data buffer. And then we also need a count. So this is going to be the size. So this is going to be new count. And once you've finished with this update data, we're going to be just returning the new data. And this is going to be our new data buffer, which is the one we'll save into the player classes table. So one of the final things we need to do is change the player joins function to account for this update function. So in the player joins function, all you need to do is override the data variable to update it to be in line with the new data buffer. From data manager, all we need to call is our database update data function that we just defined. And we can pass in the data because that's our old data, and we can pass in the player map because that's the player map that we saved in the database. Now, one final line we need to add to make all of this work is we need to make sure that we define the data size map. So underneath the connection functions in the event, we need to just add a procedure that will reference the data manager, and we're going to set the data size map and the total data size equal to, and we're going to reference data manager again, and we're going to use the configure data size map function that we defined earlier on in the video. If you remember, returned two things. It returned a buffer and a number. The buffer is going to be our data size map, and the number is going to be our total data size, which is useful for creating our new data buffer. Now, one thing I must stress with these read-write functions is that we are not calling the actual functions. We are just referencing the functions as a variable. So we don't want to actually call the functions. They shouldn't look like this with the brackets around them, because this will call the function. You just want to reference the function and store it as a variable. It should be like this. Make sure that your function look like this. So there's one final problem with our system that we've created that we need to deal with to create a fully functional saving system. And this is inside of the read-write functions module script, and it's to do with the get-read functions. Now, for example of this problem, what if I save the word tree into our database as a string? Now, you probably realize this is going to take 4 bytes of memory by now. And as you can see, I'm using the right string. I'm saving the tree string. So I've already saved this. Let's see what happens when we play the game. Well, as you can see, it prints out this awful looking number in the console. Obviously, it's not meant to do that. It's meant to print tree. So why on earth is this happening? Well, we can actually have a look in our read-write functions. We can see that 4 bytes, which is our size variable that we're comparing it to, 4 bytes is right here, and it's reading a floating point number when it's actually a string we want to read. So to fix this, we need to just double check manually if we're trying to read a string or not. And to do this, we can add a new variable up here in our parameters called isStr, is string, whatever you want to call it. I've set it as a Boolean flag. And inside of our sizes function, we want to check if the size is inside the table and it's not reading the string. And then we can use one of these functions inside of here. If it's not, if it is a string or it's not inside of the table, then it will use the read string function. Now remember, when we call the get read function, we need to change it inside of our other scripts as well, because we've added a new parameter here. So in the data manager, you'll see in read data, we use it again, the get read function. So you just need to add isStr here and add isStr as a new parameter to read data, so we can manually type in if we want it to read a string or a number. So then once I've saved my data here as a tree, I've written the string of tree into the ID of 1. When we go to read the data here, this is where I'm reading the data and it's printing out this horrible looking number. I can just add on the end of this as a parameter a true clause here, and now if I run the game with this true element here, it will run tree here instead. As you can see, it's printing out our tree variable. So stuff like this you do have to be careful of when using this system, which is why it makes it a little bit more advanced than a usual table structure. If you don't want to use this, it's fine. I will give some use cases of what this is useful for and what not to use it for. So I'm going to create a new function called save cube, and this function is just going to save a cube to our new database system. The first thing you should be thinking about when using the system for Roblox Studio is how large are the values going to be and where do I put them in the data sizes table. So you're always going to want to go into data manager, into the get data sizes function, and edit this data sizes table. So at the moment we have level and hello from the example. We're going to remove those. So the first thing I want to store is the position of the cube. So to save the position of the cube, if you follow the instructions and the help guide in the description, you'll know that we need 4 bytes to store a vector 3. It's going to be a 32-bit floating point value. The values for X, Y, and Z are going to be 4 bytes. So for each one, we're going to store 4 bytes of data. Now for readability, I do like putting a little comment on the side of it, and I like saying what they are. So for this one, it's going to be cube X value. The other two, this one's going to be the Y value, and this one's going to be the Z value. So the ID of 1 represents the X value, the ID of 2 represents the Y value, and the ID of 3 represents the Z value. Now another thing I do want to store with this is the color. Okay, I want to store a color of the cube. Well, we're going to have 3 more values. So I'll copy and paste these values here. I'm going to give them unique identifiers. So this one's going to be 4, 5, and 6. And we don't need 4 bytes to store the values. So this one's going to be the red value, this one's going to be the green value, and this one's going to be the blue value. So for an RGB value, the numbers only go up to 255. And therefore, we only need 1 byte for each one. So we can store the color in 3 bytes. Now, the final thing I want to store for this example is the name of the cube. Now, we kind of have to anticipate how many bytes we want to use to store a name. But I know that I'm overestimating, but I will never name a cube over 10 characters long. And purposefully, I've left this 7 out. So we've got an ID of 8 here to show you how this kind of ID system works. So that is all I want to store for the cube. So let's actually write and read data to this system. So back in our save cube function then, all we need to do is define the variables that we want to store. So I'm going to store the location first. So for the X, Y, Z, I've got some values written up here that I think would be fine. For the RGB value, so this is the color, I've cooked up a nice red value for us. And then for the cube name, what we need to do is do string.format and replace any characters that aren't used with spaces. So to do that, we can use the %sign with a dash and then 10 and then S. And this is the format that we're going to be using. And then we're going to take on the string. So we're going to call it cube with 3 E's. Okay, so the first thing we want to do is save the position. So in our data manager then, what we need to do is write our data, which is the function that we created earlier. So what do we need to pass into the write data function? Well, we've got a buffer, so we're missing a buffer. So to get our buffer, we can actually just call it data. So this is our current player data. And this is going to be stored in our player data module. As you remember, it's our player classes table. It's player data and then the player.userid. I guess to get the player.userid, you can pass in the player into our save cube. And that'll be a type of player. So we can do player.userid. And then obviously when we call our save cube function in the player leaves, we can pass in the player. So to write our data then, we can pass in our data buffer. First of all, we're going to save the X, Y, and Z values. So in our data manager, we save the X, Y, and Z values as 1, 2, and 3. So for the first one, we're going to do number 1, which is the ID of 1. The function is going to be buffer.write And what function is it going to be? Well, that depends on what the number is in your sizes table. Because we're using 4 bytes, that's 32 bits, we're going to be using the right 32. I'm going to use the floating point one here because we're saving negative values. We just need to pass the data in, so that'll be our X value. Now, the nice thing about this now is we can just copy and paste this 2 more times, change the ID to 2 and 3, and the values to Y and Z. So now we've saved the position, we now need to save. We can copy and paste these again. And when we're writing the data, we're going to change the IDs to 4, 5, and 6, because that is the referenced IDs in the data sizes table for red, green, and blue. And instead of our XYZ values, we would do our RGB values. And instead of the write F32 function, remember now, we are using a different number here, so we need a different function. Now, this number 1 here is going to use the write U8 function, because we're writing an unsigned 8-bit integer. Now, the final thing we need to do is save the cube name. So to write the data of the cube name, we can copy and paste our data manager thing again, and the ID is going to be ID of 8. So as you can see, we're skipping 7, and the next ID is number 8. So we're going to reference our ID of 8 here, and instead of writing to U8, obviously we're writing a string. So we need to write string here, and we can pass in the cube name. But every time the player leaves, all we need to do here is when we leave the game, save the cube, and pass in the player as well. Now finally, when the player joins, obviously we need to update the data first, so that we get the new data map with everything in, so ignore that for now. But underneath that, we need to load data. We're going to create a new function above that, load cube. So we can load the cube now, and all we need to do is pass in the data, which is going to be a buffer, because in our player joins function, we already have reference to the data. So I could just do load cube of data. Okay, so in our load cube function then, all we need to do is access all of this data and store them in local variables. We need our position variables, we need our RGB values, and we need our cube name. So for the XYZ values, all we need to do is data manager.read data, and this is our read data function. Pass in the data. We also need an ID. So we need the ID of our XYZ values, which is 1, 2, and 3. So for this one, we could pass in 1, and then all we need to do is copy and paste, and on the same line, paste it 2 more times, and do 2 and 3 there. So this line here will grab all of the data from 1, 2, and 3, and store them as X, Y, and Z. Very similar thing with the RGB values, but the reference IDs are 4, 5, and 6. Very easy to use. Now, the final one here is the cube name, and all we need to do is copy this one, paste it here, and we pass in the ID of 8. And in the function as well, we'll create a new cube with the data. So we're creating a new part. We're setting the size to 15 by 15 by 15. We didn't actually save the size, but you can if you want to. We saved the position, so we use the XYZ values, and we also changed the color to the RGB values. Now, initially, you'll probably be quite confused at why the color's black. So as you can see, we've spawned a cube here. It's black, and it's spawned right here. This doesn't seem right because the XYZ values were not at the spawn of 0, 0, 0. You can also see I've printed them down here. Everything is set to 0, and there's no cube name, which is quite confusing. But this is actually because our new database system has figured out in the update data function that there's no values stored in the old database, and it needed to set it to default values, which were 0, and there was no name stored. As a result, we got this black cube here. So what you can do now is if I leave the game, if I play now, we should get a reddish cube in a different position. And there we go. Our cube has stored in a different position here. Our name of the cube is cube. You can see all of the values that we stored in the database being presented in the print functions. A good example of using this is with Leaderstats. So I created a save Leaderstats function, which just saves a score, level, and a checkpoint. It saves the data into the IDs of 1, 2, and 3. And as you can see, for the score, level, and checkpoint in the data sizes table, I've given them 2 bytes each. So for the score, level, and checkpoint, those are the IDs corresponding. So if I join the game here, they're all 0. Let's just manually add some score and level here. So there we go. I've added some score points and level points, and let's try and save this now. Okay, all the data should be saved. So if I rejoin the game, we should have our levels. There we go. So the score and level has saved. Good example of when not to use this system is when you're trying to save data that changes over time and you don't know the size of the initial data. Now, a good example of this is going back to my Minecraft series that I did on the channel a long time ago, saving chunk data for a voxel world. You don't know how many chunks the user's going to load in. That's if you're doing an infinite world. Now, I'd love to see what you guys do with this system and see if you can make any advancements on it. This is just a brief start to the system that I made. And in the description, you'll find a guide on how to use it, different examples, and I'll put the RBXL files in the description as well for you guys to use. Hopefully you found this video useful and insightful and have a deeper understanding of the system. If you have any questions, let me know, or join my Discord server. The link is in the description below. However, thanks for watching. I'll see you in the next Roblox Studio tutorial.